Let's learn about PyTorch Profiler. So if you are coding LLM from scratch, we will learn how to use PyTorch Profiler to optimize large language model training, profile forward, backward, and optimizer steps with precise step control. So find GPU bottlenecks, memory bottlenecks, compute bottlenecks, and see where you can improve the speed of your training. And it will all be shown in a timeline view, and you can also find kernel inefficiencies. Apply these tools to debug and speed up your custom CUDA kernels, attention blocks, mixed precision operations, etc. So this is everything we will be learning today. There is a lot of examples and you can learn a lot. Let's learn about profiling. So what is profiling? By the way, guys, I wasn't posting for a few days right now. Sorry, I was flying to Beijing. I was getting settled in. I was learning everything about the city. And I also accidentally met this researcher from Tsinghua. He wrote some pretty interesting papers. His name is Bo Tianshu. I'm hoping I remember how to pronounce it. So you can check his paper about robotics and reinforcement learning. Profiling is the process of measuring the performance characteristics of your code. Example, execution time, memory usage, CUDA kernel launches, synchronization delays, and more. In PyTorch, especially with CUDA, profiling helps you identify bottlenecks in computation, example, slow layers or operations, understand GPU utilization, optimize custom CUDA kernels, debug inefficient memory transfers or CPU-GPU syncs. Tools for profiling in PyTorch. Torch.profiler, high-level API for profiling CPU and CUDA activity. NVIDIA Nsight System, so these are advanced GPU profiling and kernel level analysis. So I think we are going to use this one, Torch Profiler. But there is also this one that was deprecated, so it was there before. So we'll focus on Torch.profiler. Then discuss how to connect with Nsight. Here we see the step-by-step guide for using Torch Profiler. We have some basic examples, so we see some code. So we have model, it's a linear model. This is input, this is output. And by the way, you can screenshot this or click the link below where I will leave these studies and you can self-study. If you don't know what linear is, you can ask. So you ask ChatGPT or another AI to explain this, and this is how I imagine how self-studying works. And I think self-studying is the best way, and especially using AI and watching videos at the same time. So AI plus videos. So asking AI questions you don't understand, that's the best way to self-study and follow the videos. Then there is this input, torch rand n, and the 64 times 124. So that's gonna go in. There is 6, so this is the input. This will map to this guy, and there is 64 of those. So I guess this could be like a batch or sequence of these vectors, and each vector will be transformed from that dimension into the same dimension, so through this linear layer. Then we see this code below. So if you scroll, I'm gonna leave this chat below, but scroll down to this code, we see with Torch Profiler profile, you see some, so we are gonna pass in some activities. So torch.profiler, profiler activity CPU and profiler activity CUDA. So this, you are creating a profiling session that will record the performance of operations inside the with block. So it's gonna be whatever we define after this block. So this is the initialization, and then whatever goes after this, it will watch what each argument does. So activities tells PyTorch to record both CPU and CUDA events. Here, record shapes, true. Logs tensor shapes used in operations, useful to see how shape affects performance. With stack true, captures Python stack traces for each operation, helpful for finding the source of slow operations. So when you see a slow operation, you can look through the history to the stack of operations that led through that slow operation, so you can see where the slow parts come from. Profile memory is equal to true, tracks memory usage, For example, how much GPU memory each operation used. So we will profile memory, so we will track memory usage of the GPU. So I'll scroll all the way up to show you here. So after we have this that I just explained, we have this code, this for loop. So down below it explains the for loop. For underscore in range of 10, output is equal to model input. So we pass input through the model. So this runs the forward pass 10 times to generate profiling data. It will capture every function call involved in computing. So it will capture every function call. So as you remember, we defined the model and the input, and then we pass the input through the model 10 times, and we will save all of this data. Then we have a print statement in the end. So it says profiler dot key averages dot table, and then sort by CUDA time total and row limit 10. So what does that mean? This prints a human readable summary of the profiling data. Let's understand each part. Profiler.keyAverages aggregates data across all calls to the same operation. Example, all 10 calls to attention, or is it attention linear? I'm not sure what this atten is. I mean, attention would have double T, so I'm not sure what this is. But this is the name of the operation. So this is just this linear operation. Groups by operator name and shape. And then table, stored by CUDA time total and row limit 10, displays a summary table of top 10 most expensive operations, sorted by total time spent on GPU. What you'll see in the output table. So we have this, I guess this is add matrix multiply, or I don't know what this is. What are these two? I don't know. Yeah, matrix multiplication plus bias add. Okay, so yeah, column names. So name of the PyTorch operation. So atten ADDMM is matrix multiplication plus bias add. Okay. Self CPU, time spent on that operation itself, excluding subcalls, 12% for example, and 3% on linear. And then CPU total, CUDA total. CPU total, CUDA total, we have those two. Time spent on CPU and GPU respectively. Okay. So this is the percentage. This is the absolute like time in milliseconds. Shape, input tensor shape. Memory in megabytes. How much memory the operation used. And stack, whether stack trace is available. Again, you can screenshot this or copy this, write this, ask questions about this to AI. That's the best way to self-study. What you can learn from this, many things amongst which you have which operations are taking the most time on GPU. CUDA time total. So CUDA total, this one, okay. If there is any CPU bottlenecks, okay, so we see CPU total, so we see here names, the names, the durations. If you're launching lots of small operations, slow versus few big operations, maybe that's faster. How tensor shapes influence performance. Yeah, maybe you can just try different tensor shapes and see different performance. And then memory allocation per operation for memory bottleneck. So if you are memory bound or compute bound, you can ask AI to explain those things if you don't know. So if we now go like 4 user messages down, what are warm-up steps? So warm-up steps are initial iterations in a profiling or training run where performance is not yet representative of steady state execution. Okay, what does this mean? It just means before you start the actual training or inference, there are some things in the beginning that happen. For example, compiling CUDA kernel or creating kernels, warming up kernels. Here we can see allocate device memory, compile kernels like just-in-time or Triton, initialize cuBLAS, cuDNN handles. So these are the things that happen in the beginning. And if you want to measure some time or something, maybe you don't want to measure the time of compiling these things. You just want to measure time of training, because you want to optimize training. You don't want to optimize this compiling maybe. These can cause extra latency for the first few iterations. And then we have, so that was CUDA lazy initialization. And then we have cache effects. Those are also warm-up steps. So caches, CPU, GPU, L1, L2, shared memory are initially called. So I guess they need some time to compile and to warm up, they say. Later iterations will run faster due to memory reuse. So these things, they need to get initialized and stored into memory, some of them, store some values, etc. in the beginning. Data loader warm-up. If you're using number of workers more than 0, so I guess number of workers is number of GPUs, I think. Our first few batches can be slower due to worker startup and data shuffling. I'm pretty sure this is number of GPUs. Never mind, guys, I just asked it. So number of workers is not number of GPUs. So number of GPUs is world size. Number of workers equals to 0 means all data loading is done in the main process, Python's main thread. This is simpler but slow. Number of workers more than 0 spawns that many parallel worker processes to load data in the background while your model trains. So it's like parallel data loading processes that load data parts of data in parallel. So the main point here is you don't need to load the entire dataset. You can load dataset and start training at the same time just by loading a little bit of dataset, and then continue loading the dataset as the training is happening. But there are some caveats or issues with this. I will not read them, but if you're interested, you can ask ChatGPT or AI to explain more about this. So let's return to our main topic. So why warm-up matters for profiling? If you profile from step 0, you'll record misleading data. For example, step 0, GPU time 20 milliseconds, because it has CUDA initialization, and this is not representative because only part of these 20 milliseconds was training and other parts were other CUDA initialization and stuff. Step 1, 12, because cache not fully warmed up. Maybe it needs a few iterations, and then other steps, steady state performance. So this is the performance of the training only that we are trying to measure. How PyTorch uses it, this warm-up stuff. In this profiling schedule, so you have Torch profiler schedule, wait 1, warm-up 1, active 3. So we have phase, wait 1. This is step 0. Do nothing, avoid startup overhead, so we will not run profiler here. Then warm-up 1, it means the next step, so whatever the next step, it's gonna be step 1 in this case. Start recording, but don't save results, because we need to warm up this cache of this profiler as well, and how the profiler needs to load things as well. So we are waiting for one step, so all of the training stuff warms up, and then one step for the profiler stuff to warm up, and then active 3. So steps 2 to 4, the next 3 steps, actual profiling is saved. But this warm up in the profiler schedule, it's not just for profiler itself that needs to initialize internal buffers, hooks, etc., but also for other steps. I mean other computations. So after this active period where profiler records, there is inactive period if the repeat is not set. So what is this repeat? Repeat keyword in PyTorch. Profiler schedule controls how many times the wait warm up active cycle repeats. This lets you profile multiple windows during a long training loop without profiling everything, which would be expensive. So let's see the full signature. We have wait warmup active, and then repeat equals 2. So you see this warmup, it says here repeats x2, so total 10 steps. What does that even mean? Let's see here. So step 0 wait, step 1 warmup, 2 to 4 active, then 5 wait, 6 warmup, 7 to 9 active. So it just repeats like this. So in this case, we don't need to record every step. So this will not recording but not save discarded. So we can save on computation. Profiling everything can slow training by 2x to 10x. We can just profile 2 or more chunks across training to see how performance changes over time, if new operations appear in the backward pass, if memory grows, a leak, cache, etc. And this will also keep log files manageable. Each active phase writes a large trace file, JSON. You can collect multiple small ones instead of one giant slow one. Let's see real use case. Say you're training for 10,000 steps but only want to profile a few windows. So we wait 5, warm up 5 steps, active 10, repeat 3. So we will repeat all of these 3 times. So this will profile 3 active chunks at 10 to 19 steps, 30 to 39, and 50 to 59. So these 3 will be saved, will be active. Great for checking how backward pass changes over time, if memory usage grows, CPU-GPU overlap in early versus late training. So let's see how output file works. Each active phase will trigger a call to onTraceReady, like onTraceReady is equal to profiler TensorBoard trace handler, so this log directory. In this we'll write this log directory, so trace span 1 JSON, trace span 0, 1, 2. TensorBoard will show all repeats together in a unified window. So this is the first repeat, the second repeat, the third repeat. This is an example. We have some model. It's a very small model. We have some linear ReLU and linear, input random, target random. So we are just, and then optimizer Adam. So the profiler activities, same CPU and CUDA, and then schedule, wait, warm up, active, repeat, onTraceReady. So this is where we will save our profiler data. And this is all of the data that we will measure. And then with profiler, for step in range 20, with record function forward, we will say out, we will pass input. With record function loss, we're gonna calculate loss here. We will also have a record this function. So I will explain what this with record function means. So we have also optimizer and loss backward propagation. Oh, sorry, this is 0 gradient. For the optimizer, this is 0 in gradients, and then this is the optimizer step. And then profiler.step is tell profiler we finished 1 step. So what does this mean? So purpose of record function and then this tag, forward, backward optimization, whatever. This creates a named region in the PyTorch profiler timeline, like a bookmark around part of your code so that it appears as a labeled block in TensorBoard profiler view. You can visually separate and analyze specific stages of your pipeline, forward, backward, optimizer, etc. It helps trace performance issues to high-level code structure. So if we have this with record function forward, we have output model passing input. Nest everything run within this block under forward in the trace. And then we have this profiler.step. So if you remember, we said wait 2 steps, warm up 2 steps. So in this loop, when it says profiler step, so it's gonna see this once, and then this will tell it, okay, this is the first step. Okay, next time you see it again, it's gonna be the second step. So the first 2 steps, so 0 and 1, just wait. Okay, and then, so that's what this step is. It's this step, these steps. Thank you for watching. Check out my other videos in building LLM from scratch on YouTube. And also Bilibili. See you next time.